The MOMS mission, was that a PSLV rocket?
Yes.
But did they do a PSLV like the polar orbit?
No, that was an equatorial askew orbit.
I mean, they
It's
use
not a polar
yeah.
orbit.
So basically, they didn't tilt it.
PSLV doesn't, even though it has polar in the name, it doesn't always put into that.
But it was made for that, basically, specifically. Why does it have polar in the name?
PSLV, yeah, to launch essentially satellites, polar orbiting
it
satellites.
can use it another way.
Yes. So PSLV has like various configurations. It's not one rocket. So depending on the mission, they choose the right configuration.
Okay.
Yeah, so the GSLV, GSLV Mark III, it has nothing to do with geostationary or geosynchronous orbit.
Okay.
It launched Chandrayaan-2 to the moon.
Are they're moonquakes, no?
Yes, there are. In fact, Apollo mission had left seismometers, all of them.
They're still working?
No. They had left seismometers on the surface, which measured moonquakes. They would work for some days before they would die off. So once the astronauts launched from the surface, docked with their orbiter module in moon orbit, the leftover thing, once the docking was done, that spacecraft in which they came up in is useless. So that spacecraft was made to crash on the moon, so as to not contaminate any other part in the future once the fuel runs out. When that spacecraft crashed, the seismometer picked that up as well.
And the echoes probably.
Yes, and it echoes, yes.
Okay. So that must have given some information.
There is a seismometer on Mars right now, by the way. Yeah, that gave information about the lunar interior also.
Okay.
Because the echo would depend on
the interior structure.
Yes, exactly. And there's a seismometer on Mars right now active. It's on InSight. The lander is called InSight. It's a NASA lander. And it's not a rover mission, which is what people typically think of when they think of surface missions.
Yeah.
It's an actual lander. It cannot move.
Okay.
But it has instruments like a seismometer, air measuring station, wind measuring station, and there's a thermal probe, which is basically what it digs into the ground and tries to see the heat that is coming out of the subsurface, so as to gauge at the interior, because that would depend on the properties of the interior. So basically it's trying to monitor so many other things, which is not just geology, it's mostly geophysical properties of the planet that it's trying to gauge. And it measured some Mars quakes recently.
It did?
Yeah.
No, but then I think so for Mars at least I won't be surprised. Moon is a little bit surprising.
Yeah.
No magnetic field, which means solidified.
No plate tectonics.
Yeah.
And
where is the quakes coming from? Like, na?
Yeah. I suppose it's not completely solid. Yeah.
Yeah.
There are some smaller things here and there.
No, it could be completely solid.
But then how would the movement look like? Is it the entire thing just rumbling?
I always think about these things as like a solid ball of wax, which is hard on the outside and liquid inside. And as the heat escapes, it becomes more and more solid. Like most of the planets are like that.
So in this case, the core would probably be liquid, but a cooling core.
Yeah, even after cooling, like hot objects still will contract even if it is solid, right?
Oh, right. So that contraction will
continue
lead to that, right?
Yeah.
Okay, got it.
I mean, and moonquakes are frequent, right? Like quite
relatively. Not as frequent as.
But they come, they stop, start.
Yeah, they're frequent. In that sense, yes.
Yeah. I think so that's how they found out Earth's interior composition, right?
Yeah.
So every time an earthquake happens, seismometers all around the Earth picks up that. So depending on the intensity, and even those earthquake, when it goes through the Earth, it hits the other side of the Earth and reflects back.
Yes.
And it reflects off the different surfaces.
Yes. There's multiple
reflections inside the Earth itself.
Or vibration modes also within that, depending on lateral or horizontal or whatever that is. And so a lot of these techniques which we apply for other planets and moons is not unique in the sense that a lot of that is applied for Earth as well, because Earth is also a planet.
Exactly.
So on the moon there is also stress buildup. For example, so the contraction thing that you mentioned.
Yeah.
There is also, for example, when moon was volcanically active at one point in time. So the volcanism, the source of volcanism is the interior.
Yeah.
Typically the mantle, right? So the mantle sits below the crust.
Yeah.
Lies below the crust. And so that material is denser, which is why it's even there in the first place.
Yeah.
So when volcanism happens, that material seeps its way out. But that is denser material than the material of the crust.
Correct.
And there are layers and layers of it.
Yeah.
It's not like even one eruption event, it's multiple eruption events.
Correct.
So over time, that much amount of mantle material, which is super dense compared to the crust, it starts piling up on the crust and exerting stress. So then you start getting wrinkles, sort of like the stress wrinkles that you get, right? So the contacting thing just reminded me of this. So this leads to cracks sometimes.
Oh, okay. So the entire surface of the moon starts like getting wrinkled, like it starts bending.
Not the entire surface, the areas which
where the
yeah. So there are many areas which have had volcanism, and all those areas start having this sort
dent.
of a
okay.
Yeah.
That's crazy. I never thought about it that way. And you said like this. Okay, let me go back to the Lucy mission. You said like huge solar panels.
Yeah.
Nothing else. Like how do they go from L2, L4 to L5?
I haven't checked up on that.
Okay.
Actually, so I don't know.
Nuclear? No, but they have solar panels.
No, they are solar. They are solar powered. The power is not an issue. I'm not sure about the orbit. I didn't look into the orbital.
Juno is what?
Juno is also solar powered.
Solar powered.
Yeah. In fact, it was the first solar powered mission to Jupiter.
Acha. Just everything else was nuclear.
Yes, to Jupiter, yes.
That
so
means the
Juno
technology
basically proved that solar powered missions at Jupiter, even though you have 25 times less sunlight than Earth, you could still work out something. But they are also expensive. I mean, obviously not as expensive as nuclear power itself.
Correct.
But still expensive for something which is solar power. So, so then you have to build huge panels so that you increase your collecting area. Since this sort of a mission goes on for years and years, you need to build panels larger than you would need because the panels would degrade, especially in the space environment where you have radiation hitting the panels all the time. So you need to account for degradation of the panels, both external and internal, and accordingly size the panels.
Even electronics degrade, no, all the time.
Yes. So the electronics is taken care of separately in that sense, and the qualifications for that is like I have an article on that, by the way.
Okay.
Space grade. It's called space grade electronics.
Space grade.
Yeah, it's a term. It's a thing.
Okay.
And nearly all space missions.
They do something called like what is it? They harden it for space environment.
Yes,
that's the term,
yes,
right?
yes. The space hardening is
space
the actual term. Yes.
Yeah.
So all sorts of space missions have space grade electronics of at various levels, depending on where they are going, and that essentially means you build electronics in a very different way than you do on Earth. So as to avoid the harsh effects of the space environment.
Obviously, you can't use Intel chips inside there.
No.
So one electron coming like too fast will like just short circuit everything.
Yeah, it'll just surge. Yeah, just one cosmic ray and boom.
Boom. And then even the solar panels which are there, they have to be perfect crystals, right? Like I mean, ideally, it's a PN junction diode
right.
Acting in reverse.
Right.
So they are perfect crystals. So when there is radiation, space radiation hitting on it, these crystals actually break, right? And there's imperfections created in it. And whenever crystals get imperfections within it, like the whole the bandwidth which is there between the P and N junction, that determines the voltage that the solar panels can produce.
Generate,
that changes.
Right.
So it can go from 5 volts to 4.5 or whatever. At a particular point, like it won't be a PN junction anymore because there's so much imperfections within the solar panel. So I think the one way that they are actually preventing that, the huge solar panel, is like even if one or two cell degrade, it's not bringing down the voltage so much that it affects the operations. And the crystal is large enough that
they must have redundancy built in the system in somehow, right?
I don't think you can do that for solar panel. I'm just saying that they have made it in such a way that look, if it's a 7 years mission, they have made the solar panel that as it degrades, the voltage still remains at an operating level 7 years after.
Okay.
That's what I'm thinking.
So you're saying that you designed for something working 7 years after.
Yeah.
So if it works at that point, it works at any point before.
Yeah.
Got it.
Makes sense. It's an oversimplified thing, but like let's say the voltage degrades to half, like it's like a decay rate, like no.
So if you design the system to work with that, however minimally, then it works for any other point.
Put it in other words, for some reason, if you could somehow shield the solar panels from the radiation in space, you would need smaller panels.
Yeah.
They won't degrade. No, you can use the same thing over time.
Yeah, but then you would also need to generate your power from somewhere.
No, I'm saying that the power generated by the solar panel is less. I'm just giving a hypothetical situation where you can shield it. Forget that part. That is powered by nuclear source or whatever. But I'm saying you have a solar panel which degrades over time. And with a 7 year mission, it will degrade over 7 years. I don't think so any mission will go that long also on solar panel that far. Okay, but let's say 7 years. I'm saying that they will design that panel so that as it is degrading, by the time it's 7 years, it still has some operable voltage left.
Right.
So it's 1 volt at 7 years.
Right.
It might have started at 50 volts as soon as it started. Correct?
Right.
So I'm saying if it is shielded from space radiation, they can make solar panels to work at 2 volts right at the beginning. So you don't need that huge of a redundancy on the panel itself.
Yeah, but that again depends on a lot of the other mission requirements which may be overlapping.
Yeah.
So yeah. And the other thing is effective shielding of solar panels would require some sort of a mechanism. A mechanism which involves motion. So, and typically you need to minimize the parts which have motion, and because that still needs some power. And
wait, if it's an orbiter, then you can keep it aligned, right, all the time.
True, but in terms of let's say shielding the solar panel and then unshielding it, you would need to design it in such a way that when it's unshielded, it's not blocking anything regardless of the orientation of the craft and things like that. So, and plus the other requirements is that typically when you reach a destination, you would want to get the maximum science out of it possible initially, and then maybe have bonus sciences whenever possible. So initial demands for the power output of each instrument would also be taken into account.
Correct.
And so on. So I suppose that the initial mission requirements or at least requirements from various other subsystems of the mission probably demand that sort of a power in the first place.
Correct.
If they didn't need it, they wouldn't design it in the first place. Something like that.
Understood.
Yeah.
And this radiation which damage it, what are they mostly? Charged particles?
Yeah, primarily.
But then they can be shielded using a magnetic field.
But where will you generate that stronger magnetic field to deflect it from?
Jupiter? I mean, if you're talking about Jupiter's
mission.
Jupiter,
the problem is the magnetosphere of Jupiter itself is a magnetic field of Jupiter itself is a problem.
That's
because
trapping.
It attracts the radiation. In fact, it pours more radiation down your throat.
Yeah.
So it's sort of like the Van Allen belts of the Earth, right?
Okay.
So except worse. So
so you need to be going extremely close to the surface in order to avoid it.
Yeah, you need to go in paths which is not intersecting with the magnetic field lines.
Yeah.
So Juno's orbit is designed such that it only briefly passes through that period.
Understood.
Even then, it has to face a lot of radiation.
Yeah.
And
so you're basically saying there's a sphere. Okay, I'm just saying. So there's a sphere around Jupiter that has like so much charge funneled because of the magnetic field. And now this magnetic field is deformed by the sun, solar winds.
Right.
So it is more closer to Jupiter on the side which is facing the sun.
Yes.
And then it extends like a tail behind.
Yes, like the Earth. Yes.
Yeah. So any circular orbit will have to like go out of the belt and into the belt, out of the belt.
Yes.
That's what Juno was doing.
Yes. In fact, I believe that's what Juno is doing, and it's still running. And if I recollect correctly, the Jupiter's tail, magnetic tail on the other side, not facing the sun, is
longer.
It goes all the way to Saturn, I think.
Okay.
It's that long.
And is Saturn and Jupiter is not aligned in the same plane?
They're in the same plane, but they're not like always aligned. So
So whenever Jupiter passes Saturn, like the closest conjunction which happened and all this stuff.
No, that was the closest conjunction from our point of view.
I know.
But it was not closest in terms of the alignment of the field with respect to
Saturn.
Yeah.
So it was missing it. It didn't eclipse.
No.
But there could be a point, right? Somewhere.
Yes, definitely. So it will briefly, I think Saturn will briefly pass through.
Will the Saturn light up like the aurora belt?
I think it's the very end of the tail, so I don't think it's that because Saturn has its own magnetic field, which is more powerful than the tail part of the.
But that would affect the lights on Saturn. Saturn has its own aurora.
Yes, it does.
Thing, right?
Yeah,
it's not Borealis. I think it's something else.
Saturn Borealis. I guess. Yeah, it does have its own auroras. Yes.
Yeah.
But the interesting thing is, there's a moon of Jupiter which has its own auroras, and they're not even on the poles. It's screwed up because so Jupiter's moon Ganymede, which is the largest moon in the solar system. It's so large, it's actually larger than Mercury.
I know.
But so it has its own magnetic field. Okay. It's the only moon in the solar system to have its own magnetic field. Mars doesn't, by the way. So, but the problem is, this poor thing is within the magnetic field of Jupiter. So Jupiter rains down particles on that thing.
And then its own magnetic field is deformed. This moon ka magnetic field is deformed.
Yes.
So it can't be on the north-south. So
so there is no. So it's like those two fields interact, and effectively they sort of disconnect and reconnect somewhere near or above the equator, and that's where the particles eventually end up. So it sort of lights up like a tiger stripe sort of a thing. Like you get what I'm saying, right? Like a tiger stripe circular thing. And so that's how it lights up, and
so basically it's a weird.
It's weird.
Yeah. And like if you want to figure out how that is coming into vector calculus in 3D space of magnetic fields.
And the ice there, which is like
not
the surface is full water ice, and the ice there is, it's like, it's not even close to the water ice that you and me imagine, because it's completely radiation bombarded. So the structure of the ice has been destroyed. It's still ice. It's sort of. But it's a weird type of its own ice. Like it's its own thing, its own personality.
How many types of ice do we find on Earth naturally?
I don't know.
There are 9 types.
I think that I had heard of 7.
7.
I don't know about 9. So, but I know there's one type of ice which they call super ionic or something of the sort, which is
which is only found in Ganymede.
No. This is found elsewhere. I forget where. Anyway.
Okay, so there's one question about moon as a possible habitation for humans.
Okay. What about it as in the possibility itself?
So basically it's a general question. Hold on. Okay. Let's say you want to launch to the moon. How would you decide when to do it and how to do it, and what's the track that you take? How do people actually?
Yeah, so that's a good question actually. So it depends. It's a very intricate question. It's a lot depends on where you want to land on the moon also.
Okay.
You essentially work out backwards from there.
Okay.
So if you want to land on the moon, let's say at some region on the moon, which is interesting, and since the moon has 14 Earth days of one day and 14 Earth days of one night, you would want to maximize your day period of the mission.
Okay.
So you would ideally want to land on that site wherever you selected when you know that there's going to be sunrise at that site on day X. So now that you decided that landing site and that you decided that okay, you land on sunrise, that basically freezes your approximate timing.
Okay.
Then you start working backwards from there. To land here on this day, I will need to be in orbit around the moon for at least 2-3 days or whatever that may be, depending on your mission, in such an orbit so as to target this site at this time. And to be in moon orbit at this time, I will have to be in Earth orbit around this time so that I can fire my engines and be on the way to the moon, get captured in moon orbit accordingly. To be in Earth orbit around this time, I need to be
on the launching
at this time. And the good thing about this is if you miss a date, the same geometry repeats every month essentially.
Every 14
month.
days, right?
28
days.
28 days. The good thing is it just repeats every 28 days, more or less the pattern. So if you miss an opportunity, the next opportunity is next month. Which is not that bad for space missions.
Correct.
So, but for Mars, if you miss an opportunity, then you get it after 18 months.
After 18 months,
So I think month is fine. Alternately, there are some other things. It's not exactly rigid. For example, if you spend 3 orbits around Earth and then 8 orbits around Moon before landing, in some cases you would be able to sacrifice or increase or decrease 1 or 2. So as to compensate the early or late launch.
Okay.
So there are things you could do in between to have some flexibility in your schedule. But let's say if you miss the entire window itself, then your next window will come in the month.
So ideally what you said matters. You need to land on the part where it's sunrise and sunset. So you have 14 days.
Everything else.
After that the instruments freeze.
Unless you have nuclear power. In which case what it does is it doesn't use that nuclear power to work through the night. Instead, it suspends itself, goes on suspend mode, just like your laptop and phone. The spacecraft goes on that, and the rover goes on that mode. It uses nuclear power to stay alive in that mode, in the freezing cold, like frigid cold, minus 180 degree lunar night, Celsius. And when the day comes next time, then it turns itself on again.
Okay.
And So basically, the nuclear power is RHU, what the heating units, the radioisotope heating units.
Yeah.
They are essentially just used as heat sources, not as power sources.
Okay.
For power, they still rely on solar.
Solar, yeah.
Right. So this is sort of a good balance between
nuclear and solar kind of
in terms
usage.
of pricing and engineering and approval and so on.
But they're putting nuclear power. How much would they be using in that case?
I'm not aware actually of the numbers because it would vary from mission to mission.
Yeah, but not enough to actually.
But it lasts for years and years.
Oh, okay.
So, for example,
wait, you're saying that? But then these missions would like actually goes for years?
Yeah. So even for example, in the case of Chang'e 3, China's first moon mission, which is similar to India's Chandrayaan 2 mission, what it would have been.
Yeah.
So China's Chang'e 3 landed successfully in 2013. And it still wakes up every morning to this day, every lunar morning to this day.
I didn't know that. I don't know that.
And there's Chang'e 4, which has both a lander and a functioning rover.
Yeah.
And they landed in 2018 or 19 or something around that time.
Okay.
Yeah, 2019 January. So it's been 2 years.
Okay.
Right? So they are still functioning.
Because of this thing. The rover functions still.
For the Chang'e 4, yes.
It still does.
Yeah, it sleeps every night, comes back. It has RHU for surviving the night, and then solar panels.
I did not know this. I thought like it would have been frozen. We were discussing so much about things freezing over.
Yeah. Most missions do that, but Chinese have seemed to be like, no, we want to maximize. So
what did they put in that? China man.
Yeah, surprisingly, Chinese missions are actually one of the finest quality space grade electronics and structures you can see. It's ionic, actually.
Yeah. Okay. 2 questions over here now. When will the moon go away from the Earth's orbit?
Yeah, I think it will take quite some time. I don't remember the number though, but it's a gradual process. It's happening.
It is still happening, right?
It's still happening. It's like going away at a rate of some 4 centimeters per year.
But it is also sapping out the orbital momentum from the Earth.
Yeah, so Earth is slowing down.
Yeah, so when the Earth stops rotating, that's when the moon would stop going further away.
I guess so.
Ideally. And then the Earth moves system will go away
then
from the
sun. Tidal lock will happen. Full tidal lock.
Full tidal lock. But this is not not giving moon an extra angular momentum to start spinning. That's going to like remain as it is.
Yeah.
Why did we stop manned missions to the moon?
Politics.
Why did America never do it the second time? They did it, no? They did it 6 times, no?
No, I think the person means to ask that one time phase.
Yeah.
The second phase, why hasn't it happened? Politics. There's no incentive, basically.
Yeah. War got over.
And the way we know is very interesting. We use laser ranging.
No?
Using those retro reflectors that were left by Apollo.
Can I do that experiment?
In principle, yes.
Which laser do I need?
You'll need a pretty large laser. And a pretty large collector, more importantly, because the thing that's going to be reflected back is going to be so faint. It's like so faint. You would need a fairly large collector and be able to identify that.
So a PMT tube, probably, no? Photomultiplier.
I'm not sure. But like I'm not sure of the specifics of that.
I want to do this experiment.
They supposedly, at least they showed Big Bang Theory TV series. People do that.
Yeah. Is moon essential for life? I mean, on Earth, of course, Earth evolved.
For life on Earth?
No. Of course, it's essential for life on Earth because the life on Earth evolved with the moon in place.
In that way, yes, but I'm not sure how.
I'm saying in general, like anywhere, do you need a moon? For Mars, would you need a moon?
In what context, doesn't I didn't get the context.
Okay, let's put it in 2 different parts. Okay, first is like humans surviving on Mars.
Okay.
Would Mars require a moon for that sense? No. Okay. Animals surviving on Mars would already evolve without having moon in place. So the moment we get a moon, that's going to kill everyone. I think so.
We'll probably just confuse them. Who care to look up anyway.
Yeah. And when I say animals, I mean this like microscopic. If there are other Ceres, CERES, Ceres. What is that?
Yeah, so it's the largest object in the asteroid belt. When Pluto got demoted from a planet to a dwarf planet, Ceres got promoted from a asteroid to a dwarf planet, but nobody cared.
Okay.
So, but they should. Ceres is a pretty interesting planet. We have sent one mission to it, by the way.
Where is this planet?
So It's in the asteroid belt.
Inside the asteroid
belt? Inside the asteroid belt is the most largest and the most massive thing in the asteroid belt.
Okay.
So it's about 1,000 kilometers across. So not too small.
Yeah. What's the size of the moon?
3,000 kilometers across.
So comparable.
Yeah, somewhat.
3 times bigger.
Yeah. And so it's a fairly large object, and it is interesting because it is the mission which NASA sent there, NASA Dawn, it was called DAWN Dawn. It found hints of subsurface water on the surface of Ceres.
Okay.
By looking at the composition and the structure and.
What's the shape of it?
The shape is circular. It's circular. It's not an asteroid. Okay. It's not it was never an asteroid to begin with.
Okay.
So it's circular. It's cratered. It's a proper normal.
I heard about Ceres. I thought like it was away from after Pluto, Charon, and then Ceres was like after that. No. I'm like surprised to know that there is a dwarf planet between Jupiter and Saturn, Mars.
Yeah.
It's Jupiter and Mars between. Oh yeah, asteroid belt is there, right?
Yeah. So it's a pretty cool place, and we found evidence of lots of hints of subsurface water there, and complex minerals were found there. Organics were found there, by the way.
Okay.
So it's a super interesting world, and one which nobody cares about, unfortunately. But yeah.
Can you land something there?
Yeah, I mean, in principle, there's nothing stopping you from doing that.
No, I mean, like, would it bounce around or?
No, it has like enough gravity.
Enough gravity, right? It has it's a spherical surface.
Yeah, and if you design, exactly. And if you design something to land on it, you can.
You can.
In fact, this reminds me of a good mission, which is Mars has 2 moons. I don't consider them moons. They are like more like asteroids, which is just captured. Like there's just relatively large rocks, few kilometers across.
What are Phobos and Deimos?
Phobos and Deimos. They're just few kilometers across. Like it's barely moons.
It's rocks.
But space rocks. So Japan is building a mission called MMX, which will launch in 2024. And it will go to these 2 moons and land on the largest one, Phobos.
Okay.
So if you can land on Phobos, you can land on Ceres.
So in 2024 we'll figure out. 2026 actually. It is launching in 24. It'll take 2 years.
Yes.
Yeah. Like of all.
Oh wait! We already landed on the comet, right? There's this mission by ESA.
Yeah.
Rosetta,
I know that, but I'm not happy with Rosetta. Rosetta I wouldn't call a graceful landing. I'll give it a 2 out of 10.
It wasn't graceful, yeah. But it was a landing.
Yeah. Because...
And it was not a crash landing either. It was more like a...
Controlled...
jinx landing.
Yeah, controlled topple. That way. Have you seen like the... I mean, of course you might have seen it, but why I don't call that a proper landing is like when you look at the lander approaching Rosetta, right? It's not a circular orbit, it's triangular.
But that's okay, no? Why does it matter?
No, because soft landings, you can have a controlled soft landing with a circular orbit.
Mm-hmm.
Like with a triangular landing, the triangular orbit that is there, you're essentially pointing the lander towards it and like go. Like no. I'm saying with a circular landing, like you can like say, okay, I'm at a particular height for a particular amount of time. Now I can descend. You descend. You don't target.
Well, that is true. I agree with you there. However, the case of MMX again is interesting in that sense then, because the orbit that the MMX spacecraft will have, it's a very interesting orbit. I forget what it's called. It's some sort of an orbit where the spacecraft is actually orbiting Mars.
Yeah.
But in the sense that it's very near Phobos and it's orbiting Mars. But from Phobos, if you're standing on Phobos, it will look like it's orbiting you. The orbit shifts in that sense. It's weird. I don't remember the details of it. Okay, but essentially it means this. It's the spacecraft is orbiting Mars. But if you are on Phobos and you're looking at the spacecraft, it will seem to be orbiting you. So the motion just happens to be that way.
Okay.
And what they're doing is, so they're not letting the spacecraft even in orbit of Phobos. They're just letting the spacecraft in orbit around Mars in a way that it's always close to Phobos and it makes it look like it's going around Phobos. So you can use that as a practical pseudo orbit to plan your observations and everything, and then target a landing. So So that sort of just screws up this entire notion of a descent. I mean, this is not even a target. This is not even a descent. This is some mixed hybrid.
Phobos is Phobos is 3-4 kilometers across. 6.
No, it's something more than that. I forget the number, but it's quite a few more kilometers than that.
We can look it up. But if you have a spacecraft which is like 3-4 kilometers across, then the question of whether Phobos is like going like, are we landing on Phobos or is Phobos landing on us?
So Phobos is 22 kilometers across.
Okay, slightly bigger.
And Deimos is 13 kilometers across.
Yeah, you were off by an order of magnitude.
Yeah, but I did say quite a few more.
I think that's about it that I have. But it's like interesting.
By the way, I also have an article on the MX mission.
You do?
Yeah.
Already? Or you're making
already.
it? Already.
Yeah.
Links in the description.